Okay, good morning, Year 12. Over the next couple of days, I want you to have a look at this topic of active galaxies. And actually, at A-level, we should really call this Quasars. That's the topic we're looking at. We're going to start out looking at the general idea of active galaxies, and then we're going to fold that into Quasars in a few minutes. So the first thing I want you to do is have a look at this animation. This shows the movement of some stars in the middle of our galaxy. So the radiation sources of the stars are shown with intensities going from red down to purple, and over the course of a decade or so, you can track their movements. This implies that there is something in the middle of our galaxy. Do we already know what it is? We have mentioned it. Hopefully you can see that there is clearly an object there that these things are orbiting, or being gravitationally affected by if they're not orbiting it. But that thing doesn't output any radiation, or doesn't output the same radiation as the stars anyway. So what's going on? Well, there is, in the middle of the Milky Way, a supermassive black hole. And we end up with these big lobes of gas above and below the plane of the Milky Way, emitting gamma rays and X-rays. And it turns out that every galaxy is a little bit like this. Every galaxy has a supermassive black hole at its center. But it really depends on how large that black hole is. We'll change what it does. So the size of these black holes varies, million to a billion, or actually up to 18 billion solar masses at the center. And some galaxies, interesting things happen around that black hole. More spectacular things that are happening in the Milky Way. So, in a galaxy like the Milky Way, most of the light that we see, most of the energy that's output, is from stars. And the intensity peaks in the visible wavelengths and is distributed throughout the galaxy. You have what you think of as a typical galaxy. But there are active galaxies with an active galactic nucleus in the middle of them. And in those, most of the light actually doesn't come from the stars. It comes from glowing gas. And the intensity peaks at radio wavelengths. And it's the nucleus, the middle of those galaxies, where the supermassive black hole is, that is the most luminous. Hopefully the audio on this video will be adequate. If not, I will upload this PowerPoint anyway to Teams, so you can watch it there if you need to.
Spiral galaxies are collections of dust, gas, and billions of stars forming a flattened disk. But at the very heart of this galaxy lies a monster. Astronomers have discovered that every major galaxy has, at its core, a huge black hole, with millions or even billions of times the mass of our Sun. In a normal or quiescent galaxy, this picture is fairly serene. But not all galaxies are quiet. In some, gas and dust are actively falling onto the central black hole. This material forms a flattened disk, called an accretion disk. Friction and other forces heat the disk to millions of degrees, so hot that it emits X-rays. The disk becomes incredibly bright, outshining all the rest of the galaxy. When this happens, the galaxy is said to be active. Some active galaxies blast out beams of matter and energy, emanating from near the central black hole. These jets are powered by the accretion disk, probably focused by the disk's rotation and magnetic fields, but their ultimate nature is still not well understood by scientists. After traveling outward for hundreds of thousands of light years, the jets slow and finally stop as they ram through the thin gas outside the galaxy. Where they stop, the jets puff up, forming giant clouds of radio wave-emitting gas called radio lobes. Astronomers have learned that active galaxies like this one take on very different appearances depending upon the angle to us. If we view the galaxy edge-on, from the side, dust in the accretion disk blocks the most energetic light, and the fainter radio lobes are easier to spot. But if the galaxy is tilted with respect to us, the hotter, brighter, X-ray emitting material from the inner accretion disk can be seen. The lobes become more difficult to see. A face-on galaxy means we are looking almost straight down the jets. The intensely bright, but relatively small, accretion disk completely outshines the dimmer galaxy, and all we see is a star-like point. This type of galaxy is called a quasar. If the jets are aimed precisely at us, super high-energy gamma rays in the jets can be detected. In this extreme case, we call the galaxy a blazar. There are no hints of jets, lobes, or even the galaxy itself. All we can see is a flood of gamma rays from the very core of the galaxy. This one type of object, an active galaxy with a central supermassive black hole, an accretion disk, and jets, can appear very different depending on the angle at which we see it. It is only when we view galaxies in different wavelengths of light, radio, optical, X, and gamma rays, that their true nature becomes apparent.
Hopefully that video gave us an appreciation for how active galactic nuclei can appear to be a variety of different objects depending on the angle we look at them at. An active galactic nucleus is just the central part of an active galaxy, a brighter than expected galaxy, because of the activities of that supermassive black hole surrounded by an accretion disk. As matter falls in, it is obviously losing gravitational potential energy that is being transferred to thermal store of the infalling gas, and as it rotates, because of the conservation of angular momentum, it also produces a very strong magnetic field, and that is what essentially produces these galactic jets coming out of the poles of the galaxy, primarily made of electrons and positrons, and traveling extremely fast, sometimes called relativistic jets. This just reminds us that the angle at which we observe the active galactic nucleus determines what we see. So if it's towards being head-on, then we see a quasar. If it's directly towards us, we see a blazar. And if it's at an angle, then we see these other kinds of galaxies called safer galaxies. They're not on the specification at all. Quasars are, and we need to have a good understanding of what quasars are. We can explain how they come to be, but we need to understand a bit about the history behind them and what makes them different to other objects. So, first of all, they are quasi-stellar objects. That's what they're named as, because they look like stars. That central accretion disk is outshining the rest of the galaxies. They look like stars. Every quasar that we have discovered has a large redshift. Thinking back to last week, what does that mean? Well, it means they're moving away from us at high speed. As a reminder for what Hubbles Law is, it's showing us that the distance of an object from Earth is related to the velocity at which it is moving away from us, related to its redshift. So on this graph, h0, Hubble's constant, is the gradient of that line. And by Hubble's law, that means they must be many, many, many millions or billions of light years away from us. In fact, quasars are the most distant objects that we have observed, apart from galaxies, of course. The most distant individual objects that we've observed. And that means also that they're the oldest objects that we've observed, and they must be the brightest as well. Otherwise, we wouldn't be able to see them. By the inverse square law. Remember that as distance to an object doubles, its luminosity goes down by a factor of 4. Inverse square law. So if we can see them from billions of light years away, they must be very, very bright. Just some numbers to add flavor. You don't have to know these. Some redshifts are greater than about 7, which corresponds to a distance of about 13 billion light years, or at least a light travel time of about 13 billion years. Obviously, if they emitted light from there 13 billion years ago, they're now further away because the universe is expanding, but 13 billion years of light travel. And they have absolute magnitudes that are insanely bright, so like minus 30. Think back to the magnitude scale, minus 30 is an enormous, enormous absolute magnitude. It corresponds to an enormous luminosity. So, this is our definition of a quasar. It is a bright radio source, produces a lot of radio waves. partly because it outputs lots of radio from the radio lobes, but also because it's been highly redshifted. Those X-rays, those gamma rays, those visible wavelengths have all been redshifted down to the radio part of the spectrum. So, definition of a quasar, a bright radio source, happens to have a high redshift. In fact, we said they were all very distant. We don't see quasars particularly close to us at all. Why are they so much more numerous in the past? Well, basically because active galactic nuclei used to be really, really active, because there was a lot of gas to be falling into them. But over billions of years, all of the gas in their immediate surroundings has already fallen into them, so they get less active over time. And actually, this is a really good piece of evidence for the Big Bang theory. If the alternatives were true, like the steady state theory, which says that the universe is eternal and unchanging, then it should be the same at long distance, at far distance, as it is nearby. That's not true. We don't see quasars nearby. We only see them a long way away. So quasars are another piece of evidence for the Big Bang theory. The fact that we only find them at high distances. Okay. One other reason why quasars are important is actually because we need to be able to establish the Hubble constant. Going back to this graph here, we need to have data points to fit onto this. We talked about using type 1a supernovae, which is, of course, very important. But quasars are also important because they allow us to probe back further and further in time to the earlier universe and work out what the Hubble constant was like there. Why is it important to know the Hubble constant? Well, there's one little bit of trivia, I guess, that's on the A-level spec that we need to understand. We can work out an age of the universe by looking at the Hubble constant. We can calculate the Hubble age of the universe by assuming the Hubble constant is in fact constant. Now that's not true, which is a problem, but it's a first approximation to the age of the universe, and it's where we got our first good estimate for the age of the universe from. And we need to combine two pretty simple equations. Essentially what we're trying to do is we're trying to convert the Hubble constant into units of per second. Velocity is distance divided by time. Straightforward. Hubble's law, velocity is equal to the Hubble constant multiplied by distance. So just put these two equations together. They both equal velocity, so they equal each other. The Hubble constant multiplied by distance is equal to distance divided by time. The Hubble constant is equal to 1 over time. More importantly, time, how long it's taken everything to expand out to where it is equal to 1 divided by the Hubble constant. So, if you get your Hubble constant to the units of per second, and just 1 over that, you get a time in seconds. And that is the age of the universe, or an estimate for the age of the universe. It's the Hubble age. It is really important to get things correct. You need to convert the Hubble constant into per second. So, think very, very carefully about how you're going to do that. It isn't trivial. You need to have the correct units for velocity and distance. There is a practice question in the past paper questions that you can have a go at on this. Okay, quick quiz to end up today's information. What powers an AGN? How do astronomers find evidence for AGNs? And what type of radiation do you mostly detect from quasars? 2 minutes, scribble down on a piece of paper, check that you've understood what's going on. Pause the video here, and I'll go to the answers in a few seconds. Okay, an AGN is powered by a supermassive black hole. If there's more than one question, more than one mark involved, you might say it is powered by a supermassive black hole and the accretion disk caused by infalling matter rotating and producing a strong magnetic field results in galactic jets coming out from the poles of the galaxy. That's definitely more detail than we need here. How do we detect them? Well, we detect the enormous amount of radiation emitted across all wavelengths, so gamma, X-rays, visible, and radio. But specifically, what makes a quasar, well, is a bright radio source. A bright radio source. That's what makes it unusual. Okay, have a go at the past paper questions that are on Teams, and on Friday we'll go through the very last part of the astronomy syllabus in class live. Thanks very much, guys.